are you able to see what I'm writing? Okay, so higher order equations. So we start by defining a higher order linear nth order differential equation, and then define some terms related to the solution of higher order differential equations, and finally dwell on the examples. So an equation of the form an of t plus an minus 1 of t plus an minus 2 of t plus a2 d squared y dt squared plus a1 of t dy dt plus a naught of t y equals to g of t where the coefficient an of t is non-zero is called an nth order linear ordinary differential equation. So an of t, the nth derivative of y with respect to time, an minus 1 of t multiplied by the nth minus 1 derivative of y with respect to t, all the way plus a2 of t, second derivative of y with respect to t, plus a1 of t, first derivative of y with respect to t, plus a naught of t times y equals to g of t, provided that the coefficient an of t is not 0. We call such an equation an nth order linear differential equation. So depending on the nature of g of t, this equation can either be called homogeneous or non-homogeneous. So let's call this equation 1. So let's call this n linear ordinary differential equation. Let's call it 1. And 1 is called homogeneous if g of t is equals to 0, and it is non-homogeneous if g of t is non-zero. So if g of t is equals to 0, then 1 is called homogeneous. While when g of t is a non-zero value, then 1 is called non-homogeneous. So the homogeneous or non-homogeneous nature of equation 1 is determined by the value of the g of t, or the right-hand side, where when the value is 0, the equation is called homogeneous, while when g of t is a non-zero value, the equation is said to be inhomogeneous or simply non-homogeneous. Another thing that we can also say about 1 is that if ai of t for I to 0, 1, 2, up to n are constants, Emmanuel, so if all the coefficients ai of t is from 0 to n are all constants, then equation 1 is called, or is said to have, constant coefficients. If all the values of ai's are numbers, or simply real numbers or constants, then equation 1 is said to have constant coefficients. And then an nth order equation accompanied by the conditions y at t naught given by y naught, y prime at t naught given by y prime, y naught, y prime, and then the n minus 1th derivative of y at t naught given by the nth derivative of nth minus 1th derivative of y naught, where y naught prime, up to y naught n minus 1 prime are constants, is called an nth order initial value problem. Is called an nth order initial value problem. Similarly, we can say so y at t naught equals to y naught, y at t1 equals to y1, y at t2 equals to y2, then y at tn minus 1 equal to n minus 1, or y at tn equals to yn, where these values y naught, y1, y2 up to yn are constants, is called an nth order boundary value problem. So before even we start giving examples, it should be very clear that all the higher order differential equations we are going to solve, or what we're interested in for this unit, will be having constant coefficients. So cases where the coefficients are not necessarily constant coefficients, or there are functions involving t, will be dealt with in a different course. But in our case, all the coefficients are going to be taken to be constant or simply real numbers. So if you are doing either BSc mathematics or BSc general and you specialize in math, we'll see that such kind of problems when you'll be doing methods. So let's define what we mean by linear dependence and independence with respect to a set of functions. I know the same definition was given when you were doing SMA 203, or SUM 209 in linear algebra, but we are going still to revisit the definition of linear dependence and independence, but with respect to functions, not vectors. So definition: let S be the set of these functions f1, f2, f3, all the way up to fn minus 1. Be a set of some functions so S, this set is said to be linearly dependent so linearly dependent we can abbreviate by LD on an interval I if they are constants C1, C2, all the way up to Cn minus 1, or it can in fact even go up to Fn. You can extend this set to have n functions, so up to Fn of t. Not all zeros. So this is the key word here, such that C1 times F1 of t plus C2 F2 of t plus C3 F3 of t all the way up to Cn. This is giving us a zero function. For all values of t in I. So that simply means that when we get the linear combination of the functions, we get a zero function, provided that at least one of the constant Ci's is a non-zero value. Question? Yeah, there's an n here, correct. There's an n. There's an n here. Yeah, that's Fn of t. So that's it's very interesting to teach a very serious class. Yeah, so I have to copy the correct thing. Now, when do we say that the set S is linearly independent? What should be the condition? So that's the condition for linear dependent. So linear independence. What is the opposite of saying not all zero? Yes, all of them should be zeros. So this you can even put this one and then two linearly independent So Li, if all C i's are all zeros, i.e. C1 equals to C2 equals to C3 equals to Cn equals to 0, and this equation is satisfied. So it's more this is the same same definition you gave in linear algebra. The only difference is that in linear algebra you are mostly interested in vectors. So here we are interested in functions. So the role of vectors that you used in SMA 2 or 3, those vectors in our case they are functions, and it's the same definition. For linear independence, you get linear combinations of all the functions, and each of the coefficients in that linear combination must be 0. But for linear dependence, all the coefficients in the linear combination equation should not be all zeros. At least you need one C that has a non-zero value. So there's what we call the principle of superposition. So I give that as a theorem. The principle of superposition. The principle of superposition is simply says that if we have more than one functions satisfying a given differential equation, then you get linear combination of all those functions. The result will also be a solution to the same equation. So if f1 of t, f2 of t, up to fn of t are solutions to a linear homogeneous ODE, so this the linear ODE. So on an interval I, and if C1, C2, up to Cn are arbitrary constants, then y given by C1 f1 of t plus C2 f2 of t plus C3 f3 of t all the way plus Cn fn of t is also a solution. So that means that if we have we have n functions which satisfy homogeneous linear ODE, then if you get the linear combination of all those functions, you will also get a solution of the same ODE. So for instance, if you are given e.g., given that y1 given as a power t and y2 given as a power 2t are solutions of the equation y double prime plus or minus 3y prime plus 2y equals to 0, then y equals to c1 e power t plus c2 e power 2t is also a solution. Yes? Mm. There's no problem. So if you are given this, say this question is given to you and they may be asked you to solve it, which we are going to see it shortly, you can decide to either use t or you use x. So you can only be pinned down if they insist, if they write this one as, say, function of time. If they put here t and they put here y of t, is when it's a must you have to use t. But if they leave it open, you can either use x or t. All of them will be taken, okay? All of them will be accepted. Okay, good. Yeah. So we can quickly confirm that. So to say that y is a solution means that satisfy that equation. So y is given by c1 e power t plus c2 e power 2t. This is what is given. So we have to find the first derivative and also to find the second derivative and see that when you replace into the differential equation, the left-hand side will simplify to 0 as we have on the right-hand side. So y prime will be c1 e power t plus 2 c2 e power 2t. And what is the second derivative? Yes. So remember, when you differentiate an exponential, you just get the same exponential. So d dt of e power t is just e power t. And then this other one here, use chain rule. Okay. The second derivative C1 e power t plus, correct. So then to show that this is a solution, so let's replace. So replacing, we'll have y double prime, which is C1 e power t plus 4 C2 e power 2t minus 3 times y prime, which is C1 e power t plus 2C2 e power 2t, and then plus twice y, C1 e power t plus C2 e power 2t. So we want to show that when you simplify this expression, we get 0. But if that's the case, then it is true that that's a solution. So this will give us C1 e power t plus 4 C2 e power 2t minus 3C1 e power t minus 3 times 2 is minus 6 C2 e power 2t plus 2C1 e power t plus 2C2 e power 2t. Then collect like terms. So you'll have C1 plus minus 3C2 and then plus 2C1 e raised power t plus 4C2 minus 6C2 plus 2C2 e raised power 2t. Minus this C1, yes, or C2 for this one. So is it true that the first bracket is 0? Yeah. So this will be 0 times e raised power t. Second bracket, is it also 0? Yeah, 0 e raised power 2t. So 0 times this is 0. 0 plus 0 is 0. So since the left-hand side simplifies to 0, when you replace the derivatives of the function y equals to c1 e power t plus c2 e power 2t, then that is also a solution. And it's always true in general for any given n order linear homogeneous equation that if you have more than one functions which are solutions to the differential equation, when you get their linear combination, you must always have it as solution to the same differential equation. Yes? So you are guided by the nature of the differential equation. You see this one here was second order. So y double prime minus 3y prime plus 2y equals to 0. So it means that you need second derivative, you need first derivative, and you need the function itself for it to test whether that equation satisfies the differential equation. If we had a third derivative, y triple prime, then you'll be forced to also calculate the third derivative. Does that answer your question? Okay, good. Yeah. So let's give the theorem on existence and uniqueness. Existence and uniqueness. So suppose that Pn of t, Pn minus 1 of t, up to P1 of t and f of t are continuous functions on an open interval So given that functions Pn minus 1 up to P1, and the function f of t are continuous on an open interval I, and this open interval contains a value t naught, then when you set up the initial value problem, so remember initial value problem means the derivative and the conditions at the starting time t equals to t naught. That equation will have also a mixed solution within the same interval I. Then we define what we call the Wronskian of functions. So let us have a set S of n functions. So let's have a set S of n functions that are at least n minus 1 times differentiable. Then the Wronskian of S, denoted by W of S, is given by is simply the determinant W of S is the same as the determinant of F1, then F2, and then F3, all the way up to Fn. These are straight lines to mean determinant. Then second row becomes the derivative of the first row. The next row becomes derivative of the previous row. All the way up to the nth minus 1 derivative. So the determinant formed by putting the functions on the first row, differentiating the second row up to the time of n minus 1 to the derivative. So as appetizers, find the Wronskian of sine t and cosine of t. So to solve this, so we let S be the set of these two functions, sine of t and cosine of t. So which means the Wronskian of S will be the determinant of, so the first row, you write the functions. And because we have only, so this is like F1, this is like F2, we'll only need the first derivative to define that determinant. So the derivative of sine is cosine. Derivative of cosine is negative sine. Let's compute that determinant. -1, correct. Yeah, because we have sine times minus sine is minus sine squared. And then minus cos times cos is cos squared. Then you factor out negative. Sine squared t plus cos squared t is 1. So 1 by -1 is -1. 2, what if we have s to be e power t, t e raised power t? Can you find the determinant of that set? The Wronskian of that set? Zero? Sure? Okay, so let's confirm together. So we'll have Wronskian of S will be, so the only two functions. So you have e power t, t e raised power t. So the derivative of e raised power t is e raised power t. But what is the derivative of t e power t? Which rule do you use to differentiate that? Product rule. So u prime is 1. So times this will get e power t plus when you differentiate e power t, you get e power t times u, you get t e power t. So the determinant will be e power t into e power t plus t e power t minus e power t times t e power t. So when you expand this e power t by e power t, e power 2t plus t e power 2t minus t e power 2t. That simplifies to e power t 2t. Okay. So because the second and the third term cancels out. Number 3, what will be the Wronskian of these two functions, 2t and 4t? Zero. So you should check that the Wronskian of S is 0, correct? And then number 4, what will be the Wronskian of these functions? T, 3t minus 1, minus 6, and then 1. And number 5, Wronskian of 1t and t squared. So once you do that, then you'll have a small break. So number 4 is t, 3t minus 6. This is 3t minus 6. The last function is 1. So there are 3 functions, t, 3t minus 6, and then 1.